Hope you got a few people attending today. Hopefully we got some new people in today. If you're new, great, good to have you. If you've been here a couple times, that's even, or if you haven't been here before, that's even better. I like to try to get as many people as possible on these. These are fun and entertaining. Welcome to the Rolls Battery Engineering webinar. My name is Steve Higgins. I'm the Technical Services Manager of Rolls. I'll show you my contact information here in a second. Just to let you know that this information is downloadable. We do have some of these, most of these are actually already posted on our YouTube channel. But if you want to take a look at these, and as well as about 30 other videos that we currently have, you go to our YouTube channel. I also have a shared drive on Google Drive. So all these presentations, a lot of these presentations and documentation and things are located on our Google Drive for quick access if you have access to Google Drive. This is the link, tiny.cc roll share drive. So that's the link if you want to if you want to just go to this tiny.cc / rolls shared drive, all one word. Or if you want the link, you can send me an email, steve@Sarette.com. I'll be more than happy to send you the link. All right, my contact information again. My name is Steve Higgins, and my email address is steve@Sarette.com. Come on, sometime today. steve@Sarette.com. My phone number at the plant, 902-597-4020. Feel free to give me a call. Remember, in times not COVID, I do spend about 200 days a year on the road, so sometimes emailing is better than phone conversations. My mobile number is the 206 number. I am actually based in Western Washington in the US, and of course my toll-free number is 1-800-681-9914, extension 4020. So if you have any questions, feel free to give me a yell. I'll do what I can to help you out. All right, about the interface a little bit. I like to talk about the interface because just because we have people who aren't quite familiar with it. This is a screenshot of that interface. Please ignore the dial numbers, and access codes are going to be different than what we're looking at now. If you go ahead and click on the questions pane and then enter your question here, and we'll be more, what I'll do is I will read the question and answer the question for you. In the past, we've tried to do mics. Unfortunately, with the microphones, that gets a little crazy with the feedback, and a lot of people have stuff going on in the background and you can't hear it. So it makes it more difficult to do these presentations that way. So do that. We try to keep these to 60 minutes, try to keep everybody engaged as much as possible. I will fill in with secondary stuff if we don't have any questions. Again, audio questions just don't work out very well. So before we started, when we announced this, I got an email this week that I want to address a couple things about batteries in general. Basically, I want to address parallel connections, and the gentleman's question was, when charging with two parallel battery banks, when charging, what is an acceptable differential current between each parallel set? This customer, he was charging at 65 amps. He has 34 amps going into one parallel string, and he has 31 amps going into the second parallel string. That is actually a really good question, and it's a advanced troubleshooting tip that I use, that sometimes if you have multiple parallel strings and we're talking about the system, we're talking about a specific system or a specific issue, you have multiple parallel strings, I will have you look at those currents to see what's going on with them. And the reason for that is that sometimes you can get different currents. Now, for example, this is an example of what not to do with your solar system. This is 5 parallel strings. It's actually was written for the old S530 or S5, the beginning S550. 428 amp hours of batteries configured in 24 volt. You got 5 parallel strings. Let's say you have a 100 amp current source. Okay. Each battery has an internal resistance of approximately 0.0144 ohms of internal resistance. Okay. So the overall string has an internal resistance of 0.00576 ohms. And that's not including your cables and connections and stuff like that. Those can add more internal resistance to your system. So, okay, got a double screen there for some reason. So, oops. So ideally, if we've got a 100 amp charging source, okay, and everything is perfect, ideally we're going to see about 20 amps of current across each battery bank, across each parallel string. So internal resistance is all the same. We're going to see roughly around 20 amps of current across each battery. Now I'm going to want that to be about 10 to 20%. And the reason I'm going to want that to be about 10, right, my maximum differential is going to be about 10 to 20%. And the reason is if there's a problem with these batteries, what can happen is you'll actually see if the resistance of the battery goes up, you're actually going to see less current going into the battery. If the resistance of the battery goes down, then you're actually going to see more current going into that parallel string. Okay, so for example, on this particular example, if we have all of our internal resistance, this string is 0.005, this string is 0.007, this string is 0.005, this string is 0.005, and then the last string is 0.005. This string here has a little bit higher internal resistance. And so what that's going to cause is it's going to add current to this string, and your current and that one string is going to drop off. So what's the problem with that? The biggest problem with that is the first thing they should tell you is there's a problem with either connection or battery in the string, okay? And so if you have 2, 3, 4 parallel strings of batteries, it's a good idea to look what these currents are just by putting a current clamp meter on your negative lead, running a charge into the batteries and watching that current drop. Because I mean, the biggest reason for that is that one of these batteries, either we have a connection on these batteries that is faulty, or we have an actual battery that is having problems. And so if you go and do a further evaluation, you might find out that one of these batteries has got a dead or a failing cell or a bad battery connection, and that's going to cause a problem for your system down the road. That's not something that you want to stick around with. So that was the first question I had. That was actually emailed to me yesterday. I already answered the gentleman. He's not here, it doesn't look like, but hopefully that question benefited the rest of everybody here. Does anybody have, now is the time to enter questions if you want. If you don't, then what I'm going to do is I'm going to go back to using you guys as guinea pigs, and we're going to talk about some other issues. And so when I get so I'll go ahead and get to the screen I was going to talk about. Just one second. We'll talk about load testing temporarily. And so load testing is important, especially for AGM batteries or gel batteries. And so where it comes into play is with an AGM or a gel battery, you can't look at the specific gravity on an AGM or gel battery. So it's virtually impossible to tell what the state of charge or the status of that battery is without looking at the load test. And basically what a load test is applying a load to the battery over a period of time and measuring the cell voltage of the batteries. So on flooded batteries, sometimes you'll get good specific gravities across the batteries. All the cells will look good, 1260 to 1270, everything will be fine. But as soon as your customer turns on a big motor load or they turn on a load in the house, one or more of the batteries, the cell voltage drops off. And so if it's a 6-volt battery, it might drop to 2 volts. It might drop to 3 volts or 4 volts over that period of time. And that could be an indication of a cell that's in the process of failing. It can be an indication of corrosion on the plates from using bad water. It can be an indication of the cell in the future or the past has been left dry at some point. They've added water. Basically, it's indication of a cell failure. It's not an indication of a warranty situation. Could be a warranty situation, but it also could be a non-warranty situation. Again, with AGMs or gels, it's very difficult. You can't check specific gravities, and so sometimes it's a good idea to load test the battery bank. Systems that people have had me come out and maintain that are AGM batteries or gel batteries, I typically will tell them that you want to load test at commissioning. You want to load test at 6 months to make sure you're charging correctly. And then from there, you want to load test every 12 months after that to determine if you've got, above 75, 80% capacity in your battery bank. The problem is that in the field, it's very difficult to do a load test. The typical load test you need is what's called a linear load. And what a linear load does is it places say you wanted to put a 100 amp current load on the batteries, okay, at 48 volts, 100 amps at 48 volts, it'd be roughly 4,800 watts of load, roughly about 5,400 with the inverter losses and all the other losses you could calculate. The problem is as the battery voltage drops, that current goes up. So it's an Ohm's law thing. So as soon as when battery voltage starts at 51, 52 volts, and it starts sagging down to 46, 47, 48 volts, what'll happen is your actual current draw will go up with those lower voltages. And so what a linear load does is it changes the load as the battery voltage drops. So there's a program logic controller in there that regulates, if you want 100 amps load, it keeps 100 amps load during the entire test. So it'll actually reduce the current draw over that period of time to hold the load at 100 amps versus watching the load go up. And so you want to be cautious with that. So the problem is that with linear lows, is they are about the size of a 70s, 80s, 17 cubic foot refrigerator. So they're approximately 4 to 5 foot tall, actually about 3 to 5 foot tall. They are, about the foot space of a small refrigerator, and they will run you between $25,000 and $100,000. They are not an inexpensive device to purchase. So you want to be careful with it. Now, what you can do is you can use the house to do a load test. And I've done this on many occasions. When you go out to a site and you need to do a load test, to do so, you're going to need time. Load testing can be time consuming. The heavier load you run, the less time you have to worry about. The lighter the load to run, the better your results are going to be. The longer it takes time to run that. So a couple of things you need to have is you need a current meter to ensure discharge current remains close to the battery rating. And then you want to monitor current voltages in half-hour to hour increments, and then log those measurements. And so basically, for that 4 to 10 hours, you're hanging out near the battery bank, taking voltages, maybe spot checking a specific gravity or two, checking your connections to make sure they don't overheat, making sure you've got enough ventilation in the battery bank room. And so this is a test that does take some time and some patience to do. So the first thing that you want to do is you want to determine the C10 discharge rate of the batteries. So if you had a single series string of S6 L16 HCs, which are the equivalent to the old S550s, so you had 8 of them configured at 48 volts, your discharge current would be 40 amps, basically 40.5 amps. Okay, and so I'm going to go ahead and underline that here, 40.5 amps. If you had 2 parallel strings, it would be 80 amps. If you had 3 parallel strings, it would be 120.15 amps. Okay, again, I apologize for my chicken scratch. Hopefully you can read that. While you can test all 3 parallel strings together, or all the strings together, it's not really the most accurate test if you're having to measure a whole bunch of stuff like that. So I would suggest that you separate your strings and test each string independently. The other thing you've got to consider is if you're trying to run 120 amps of current, that's roughly around 6,000 watts of load at a 48 volt battery bank. Okay, that's a lot of load. Okay, so you definitely want to make sure that you test each string independently, otherwise you're going to have issues. Testing at higher discharge rates is okay, but you're going to need to take voltage measurements much faster. So if you're doing this work by yourself, it's going to take time. And so you want to be able to catch the voltages fast enough and record those voltages. Typically what I'll do is I will say, okay, I'll start a tape recorder, or basically I'll put my phone in voice record mode, or I have an MP3, portable MP3 recorder that I stick in the battery room, and then I'll talk my way through it. I'll say, beginning a load test starting at 4:42 a.m., PV array is shut off, and battery bank measure, and then I'll go preload testing, cell 1's this voltage, 2, 3, 4, all the way to 24, and then I'll walk my way through that, and then I'll record it. I'll listen to the recording at a later date, or when I'm doing the documentation for my testing, I'll listen to the recording and log that documentation. All right, so basically what you do is you apply your loads. Once you apply your loads, you just turn on loads. And so in the past, I had a house that was highly efficient. The only thing they didn't have that was, and I'll show you an example here toward the end. The only thing that they didn't have that was efficient was they had a 10-ton air conditioning unit on the roof. And so what I did is I turned it on and I set it to 16C or 60 degrees Fahrenheit and opened up all the doors and windows. And so that kept the air conditioning compressor on as much as possible. You'll see the example of that here in a bit. And then of course, every 30 to 60 minutes, you're going to take voltage readings across each battery, and we'll step through that here. So this is just an intro. So we'll step through that here in just 1 second. All right. So when you're doing this test, you're only discharging to 50%. Okay, you're not doing a full 100% depth of discharge, and so you have to keep in mind that you're doing that 50%. So if you're loading at the 10-hour rate, you're going to do 5 hours of load. You're going to discharge those batteries down to about 1.75. Actually, you're going to discharge those batteries to about 1.75 to about 1.8 volts under load. So if this is a 6-volt battery, just start at 1.8 volts, which means I'm going to drop the battery voltage, each battery cell, down to 5.4 volts under load. That's not, depends on how much load you're running. That's not a big problem. The issue is that when you get down to that 1 point, so you drag down and your first battery is hit 5.4 volts. At that point, I'm going to shut off all the load. I'm going to give the batteries 10-15 minutes to recover, and then I'm going to go through and recheck an unloaded cell voltage measurement. Okay, and so what that'll do is what you're looking for the batteries to recover to at least 2 volts per cell. That means, because 2 volts per cell resting voltage is 50%. And so if we did a 4.5 to 5 hour test at roughly that 40 amps per string, those batteries are at 100% capacity. If you did a test, if you only lasted 2 hours or 3 hours, then your batteries are at roughly 50, maybe 45 to 65% capacity, depending on the voltage they drop to. So what we're looking for is on a 2-volt cell, you're looking for differences in voltages. So 2-volt cell, you're looking for 0.2 to 0.3. On a 6-volt cell, you're looking at 0.4 to 0.6. On a 12-volt battery, 12-volt monoblock, you're looking at 0.6 to 0.9 volts. So you're looking for that difference of voltage over time. So we'll address that in a second. Amp capacities are based on specific gravities of a 1280 rated capacity. So if you're at 1265 specific gravities, you're going to be minus 5%. If you're at 1250 specific gravities, you're going to be minus 10%. So you got to take that in accounting. So if you're doing load testing on a battery that's in a discharge state, where you can only get the specific gravities up to 1250, you've lost 10% of your capacity right there just based on your specific gravities. You have to take that in consideration when you're doing this load test, because if you don't, you're going to get false information, and that's going to cause a problem. All right, so here's what a passing load test looks like. All right, so this is what a passing load test looks like. Test begin, we're going to call them all good. So we've got cell voltage, we've got 12 cells, 24-volt system. You've got a cell voltage of basically 2.13 volts all the way across. Not a big deal, right? That's kind of what we expect. We at least expect that 2.13 volts across the entire battery bank. All right, so hour one, we're measuring our voltages. We have 2.11, 2.11, 2.10, 2.09. I would expect to see a little bit of a variance between the cells. Remember, not all cells are created equal. So you need to take into account that that's sometimes going to affect what you're dealing with. So I'm not worried about these. I'm not worried about these lower numbers at this point in time, because there's not a huge difference in cell voltage. Okay. Next screen. So now, you know, we're at about the same. We're at about the same numbers. Not a big deal. Okay. This is kind of what I would expect. You know, so our numbers are all relatively 0.1, 0.2 volts apart. Again, this is what you're going to see when you get a healthy bank. It's not a big deal. And so as we go through, we've got a full 5 hours. Our cell voltages went down to 1.86, 1.85. You know, so we did a full 5-hour test and we only dropped to 1.85 volts per cell. Okay. At that point, I'm going to shut my load off. Everything recovers back up. I've got one cell that recovers at about 1.99, so it might be a little bit lower capacity, but we didn't get to that bottom end of 1.8 volts per cell. Okay. So if I got 5 hours, okay, and the batteries didn't drop all the way down below, and my battery voltages pretty much all recovered to 2 volts per cell plus or minus 0.2 volts DC. Actually, that would be 0.02 volts DC. Then these batteries are 100% plus capacity. Okay, so that tells me the battery bank's good. The battery bank I currently have in my garage, it's almost 18 years old. It'll actually be 18 years old in January, or not January, but July. That battery bank gets to about here, about hour 3 before it collapses. So that battery bank it's actually between hour 3 and hour 4. So that battery bank is actually roughly around 70 to 75% capacity. It just happens with age. Batteries get worn out, happens with age. There's not a whole lot you can do about it. All right. So load test fail. So start with the same thing. You charge them up as best as you can go. Sometimes you can't get them all the way up to 2.13, you know, 2.10. That's not what you're looking for. You're looking for a difference. You just need to make sure that that lower capacity is taken into account. So we start doing our load test. After the first hour, we immediately have an issue. So cell 5 is already exhibiting issues. It's almost 0.1 volt out of tolerance from all the rest of the cells. And so as we go through this entire 5-hour test, 2.07, 1.98, 1.73, 1.63, 1.43. That is a cell that is struggling to keep up with the rest of the cells in the battery bank. Okay, and so this is what a load test is. So you shut the load off, it does recover and it does come up to 1.74 volts. But cell number 5 at this point, let's say the battery bank is, it's 2 or 3 years old. Okay, if it's 2 or 3 years old, you submit your specific gravity test and you submit this data, we're going to cover it under the replacement warranty. If it's 6, 7 years old and all the other cells are testing okay, then let's do warranty. Yes. And so 6, 7 years old, it's of course out of warranty. We're not going to cover that in a warranty. But if it's only 6 to 7 years old and the rest of the cells look like this, you get the 2.01, 2.01, 1.9, and they all held, I would replace this cell and move on. Because basically what you're doing is you're sacrificing that one cell for the rest of the battery bank. Now let's say you had, I'm going to go ahead and erase some of these writing. Let's say you had some of this, let's say you did, let's say this drop, let's say this cell dropped to 1.5 and this cell dropped to 1.4 and this cell dropped to 1.8 and this cell dropped to 1.75. Okay, now you have 1, 2, 3, 4, 5 cells out of 12 that are basically in the process of dying. Okay, in this case, I would not just replace one. If this battery bank is 6 to 7 years old, more than likely that battery bank has hit end of life. And so what you need to do is you need to inform the customer that they could probably limp through the summer on something like this, but on these batteries, they're not going to limp through the winter on. They're going to have to replace those batteries pretty much within 2 or 3 months at the most. If it's the summertime, your solar may help you keep the batteries up because of that daily good solar charge, but you're probably not going to survive through a winter on these batteries. If you try to, more than likely what's going to happen is that they're going to freeze. Because remember, batteries freeze due to cold temperatures. Batteries, the water that the electrolyte is made up of 68% water and 32% sulfuric acid. If you've got these cells, they will discharge faster, which means the cells will discharge faster, which means the electrolyte will turn to water faster, and that water freezes at 32 degrees Fahrenheit or 0 degrees Celsius. If the specific gravity is just dropped to a 1.220, they will freeze at -6 degrees Celsius or around 20, I think it's around 22 F. Okay. I'm still working on my metric temperature. So I've got the distances figured out, but the metric temperatures, yeah, I'm still working on it. Especially when you start talking negative temperatures. So load testing is important, especially for AGMs and gels. That will help you troubleshoot that stuff. For flooded lead acid batteries, it can be important, especially if you have a battery that's in the process of failing and it's borderline. Specific gravities are all good, but whenever the customer kicks on a load, something bad happens. So that's a good thing to do that load test. So at this point, do I have any questions about the load testing? I've still got a few people in the room, not as many as I'd like to have, but I've got a few people in the room. I don't see any questions yet, unless there's something going on. I hope that's not the case. If it's not the case, then what I'll do is I've got about 25 more minutes to go. I will pause here and wait for some questions while I try to bring up another topic. I've just recently put together some slides for another training course, and I'm going to go ahead and use you guys as guinea pigs on. We're going to talk about common system sizing mistakes now. I'm not sure if we've talked about this. I may have talked about this, but I've changed the format of the slides a little bit, so we'll talk about it now. Here we go. So the number one mistake that I've seen over the last 25 years of being in the solar business is oversizing of the battery bank. In the US, they have a saying, or we have a saying in the US, go big or go home. Go big or go home does not apply to batteries. And the reason for that is that the bigger the battery bank that you install, the bigger the charging source you need to install to get it properly charged within a certain amount of time. One of the biggest problems I see, especially for full-time off-grid homes, is the client goes out and they've got a 2,000 square foot home or a 3 or 4 bedroom home. They put on a 3,000 watt solar array, and then they want 7 days of autonomy on the battery bank. And so the battery bank's 3,000 amp hours. The problem with that is that 2,000 watts of solar at 48 volts is only going to generate around 25 to 30 amps of nominal current. If you try to charge a 1,000, 2,000, 3,000 amp hour battery bank with the 40 watt, or 25 to 40 amp service, it's going to take days to get to full charge without properly. I mean, it's going to take days to get to that full 100% charge, and that's not good for the battery bank at all. What will happen is that battery bank will sulfate severely over the first few years, and the battery bank will die. So it's not a problem. It's not something you want to get involved with. Too many parallel strings. I personally will not do anything more than 2 parallel strings in a battery bank. 2 parallel strings of batteries is nice to have for, say, the S6L16s. That way, if you have one battery that's got a problem, you can drop one of the parallel strings out and operate it. Anything over 800, 900 amp hours of battery capacity, I will typically go to 2-volt cells, which means if it's a 24 volt, I've got 12 cells in series. If a 48 volt, I've got 24 cells in series. The reason for that is if I do have a single battery that does fail, something goes wrong with it, then what happens is I can pull that one battery out and operate at 46 volts instead of 48 volts, and I can continue to operate that way. So you want to be really careful with that, because if you put in a huge battery bank and you don't have the renewable sources to charge it, you're going to have problems. Shoehorning product. Sell the right solution to the job, not what you have in stock. Try to keep your stock levels as low as possible first. It's a good business decision, especially for you installers. But if you try to sell 6-volt L16s and you sell 8 parallel strings of 6-volt L16s because that's what you got in the warehouse, versus selling a couple series strings or a couple series parallel strings of 2-volt cells, then what ends up happening is that you're going to start that customer, if they're not doing their maintenance, they are going to have serious balancing problems just 1 to 2 years into the installation. So you want to try to avoid that. So sell the right solution to the job. Get the right charge controllers. Get a charge controller, get a charger that you can program. Most of the solar batteries today require a higher charging voltage, and if you're not properly charging the batteries, you're not getting that reasonable charge into the batteries. What's going to happen is the batteries aren't going to get fully charged, and then that's going to kill the battery bank. So don't shoehorn product into the battery banks. Not understanding battery C rates. Okay, in North America, Latin America, some places in Africa, even some places in, well, not Europe, but in North America, generally, we size to what's called the C20 discharge rate. That means if you look at the spec sheet of the battery, the spec sheet of the battery will give you that C rate. And so the C rates of all the batteries are you got a C100 or C125 or 120, all the way down to a C1 rate. What that means is that when you load a battery, okay, I could take a S6L16HC and I could load that S6L16HC at about 20 amps a load, and I'm going to get 20 hours before the battery is 100% depth of discharge, i.e. 10 hours to 50% depth of discharge. I take that same battery, I charge it back up to 100% full, and then I discharge that battery at 70 amps of current. Now that 70 amps of current is going to reduce the overall capacity and size of that battery. That battery at 20-hour rate was rated at 445 amp hours, but at that 70 amps of current, now it's a 5-hour battery rated at only 356 amp hours. Okay, so basically what this is the C rate is the heavier that you load a battery, the less battery you have. Okay, and it's important to understand that. It's important to be able to explain it to your customers, because if you design their system to a 20-hour discharge, okay, which is 10 hours of use at 50% capacity, if you design their system for that 20 hours of discharge or 10 hours of discharge, what ends up happening is that customer is going to add loads, and if they increase that load, they're going to shorten the life of the battery bank. They're going to shorten the capacity of the battery bank, so the battery bank's not going to work as advertised. Okay, so you want to make sure that you take care of that. If you're an end user or if you're a installer, make sure you understand that. The next thing is making sure you understand the product that you sell. This is a little bit of a pet peeve for me, and I apologize, but for those of you who are installers, you are getting paid to install a product. You need to understand that product better than the tech support people at those product manufacturers can support you. Over the last 20 years, tech support in the renewable energy business has stagnated because a lot of these companies have gone public, and when they go public, it's all about the bottom dollar, bottom line. And so a lot of tech support departments suffer from this. I hear it every time I go to shows. I hear it every time that I look at the support forums. Everybody calls up and says, yeah, you get, 60% of the people say they had a horrible experience with tech support. The other 40% of the customers say they had a great experience with tech support. It just depends on who you get and their confidence level of the day. And the other thing you got to keep in mind is tech support in general, they are the punching bags of the businesses that you're talking. So if you're calling Outback or Schneider or Magnum or Rolls Battery, they are the punching bags. They are any tech support department. Those guys, they get beat up on a constant basis. So if you're installing an Outback, with a FlexNet DC, make sure you understand how that FlexNet DC works. If you're installing a Schneider charge controller, Schneider inverter, or a Magnum BMK, make sure you understand how those products work. A lot of people, when I tell them that if you set the Schneider amp hour capacity to the actual C 20-hour rate capacity, that's actually going to possibly damage the battery, because the way that the Schneider determines a full 100% charge is if you set it to 445 amp hours, that means at 8.9 amps of current for 1 minute. So when the current going into the battery, that sets the end amp setting. So when the current going into the battery drops to less than that 8.9 amps of current, for 1 minute, the charge controller thinks the batteries are full. And a lot of battery manufacturers want that below 8.9 amps for a full 60 minutes before we assume the batteries are full. And so the reason I threw Magnum in there is their BMK does the same thing. The Outback battery monitor, it allows you to set the time. You set that target voltage, and then you set the time, and then you set the what's called a battery charge factor percentage. That comes defaulted at 94%. There's not a battery on the market that's a lead-based battery that does 94% efficiency. Most lead-based batteries start out at 80 to 85%, and after about 2 or 3 years, they'll lose efficiency about 1% per year after that. So make sure that you understand the product that you sell. In 1995, when I started the solar business, solar panels were about 80 to about 100 watts, and they were about $8 to $12 a watt. Nowadays, you can buy a 360 watt module for about 75 to $1 a watt, depending on the manufacturer. you can buy the 260, 300 watt modules for, 45 to 60 cents a watt. There is absolutely no reason whatsoever, unless you don't have installation space, that you cannot put on a large enough solar array to not have to run your generator on a constant basis. You have to think of it as free energy. When you go out and install, 4 or 5, 6 kilowatts of solar on a 800 amp hour battery bank, just think 8 months of the year, you're not going to run your generator. You're not going to burn diesel at $3 a gallon, or $1.20 a liter, or even higher in some places. So there's no reason not to oversize the solar in today's world. Consider the loads used by time of day. If you have a client that's primarily at home, say that client works from home, you need to take into account that they are at home and they're working from home. If you size that system with the assumption that they're not in the house and that solar is going to charge those batteries during the day, you're going to be in for hurting, because that client's not going to do that. The client's going to use that load, that solar, during the day, and at night, those batteries, after the first couple of weeks, those batteries are going to struggle to stay charged. So keep that in mind. Solar production is different throughout the year. Your solar production in some places is better in the winter than it is in the summer. Other places it's reversed. It's better in the summer than the winter. And so you need to size the solar production based on the worst case, not the best case. And so you want to try to avoid that. Not understanding the pluses and minuses of different battery chemistries. Listed here are calcium batteries or lead-based batteries, but when you consider them all, a lead antimony, which is typically your flooded battery, wants to cycle, wants to exercise. If you leave it set at a high state of charge over a long period of time, what will happen is it'll look like it'll work fine, but it'll lose capacity. Calcium batteries, like an AGM battery or gel battery, those are typically a lead calcium based battery. Those batteries are meant for telecom applications. Those batteries are meant to float and stay and float pretty much 24 hours a day, 7 days a week, 365 days a year. They won't lose capacity, okay? But they don't cycle as well as flooded batteries, typically 1,500 cycles versus, 1,400 to 5,000 cycles. Lithium battery, lithium ion, they have a really high thermal runaway temperature. So if you do have a cell that fails, they'll run away at over 250, 300 degrees Celsius. Lithium ferrophosphate, LFP or LiFePO4 batteries. They don't cycle as well as lithium ions, but if you do have a thermal event, a thermal runaway issue, they won't get any warmer than 70 degrees Celsius. And so there's definitely an additional safety factor. It's one of the reasons that we are manufacturing a lithium ferrophosphate battery instead of a lithium ion, because it's a safer battery to use in general, in our opinion. So understanding the different chemistries, make sure you choose the right chemistry for your installation. Just to give an example, you've got a couple who has a cottage, and on, say, the cottage country in northern Ontario, they're there for 3 months of the summer, and then the rest of the year they're not there. Would you install a flooded battery, a calcium battery, an AGM or a gel, or a lithium battery? In my opinion, that would be definitely it would be a calcium, like an AGM or gel, because they're probably not going to do maintenance. They're not going to be there for 6, 7 months of the year, and that battery is less likely to freeze. Okay, lithium battery, it will shut off due to temperature. If temperature is low, so if they leave the system on, it'll shut off. It'll also handle the 6 months without being charged. So you can shut the whole system off, drive away. You don't have to worry about your battery when you come back in 6 months, because it's only going to discharge around 10, 15% at the most during those temperatures. While a flooded lead acid battery, you're going to need to top it off with water about every 1 to 2 months, even if you lower the charging voltages. or you're going to risk drying the battery out. But it also has the possibility of freezing. So you have to take those things in consideration when you install and design a system. If you don't, you're going to eventually back yourself into a corner, and you're eventually going to cause problems with your system and problems with your business. And if you're an end user listening to this, you have to consider how you're going to use that system. If you're going to live on that system if you're going to live in that house 12 months a year, then my option would probably be a flooded lead acid battery, or if you've got the money, you can go with the lithium ferrophosphate batteries, because as long as you take care of them and you're not doing 100, you're not beating the living daylights out of them, and you have heating to keep them warm in the winter time, because they don't work very well in the winter when they're cold. You can make sure that those batteries stay okay. So again, talk to your installers, talk to the folks in distribution. If you have any questions, I will give you give me a call. I'll give you an opinion. I can't guarantee you like that opinion, but I'll give you an opinion. So the next one, trying to get too accurate on system sizing. I've been guilty of this. Everybody who's done a system design in their life has probably been guilty of this. You want to try to avoid trying to get too accurate on sizing a system, because if you do, what can happen is you can literally sit there and spin your wheels, and it's quite painful after a period of time. So the important thing is to miss high, not low. If you miss low, you're going to have to add parallel strings down the road. If you miss high, then you're gonna allow that system to grow for that customer. So I've talked about temperature a little bit, not taking account both warm and cold temperatures. Warm temperatures of just 35 degrees C, if it's on the battery 12 months a year, 7 days a week, 365 days a year, 24 hours a day, you're going to lose your cycle life by 50%. Generally, for a system, say a system installed in Puerto Rico in the Caribbean somewhere, those systems spend 5 to 7 months a year at greater than 35 degrees Celsius. So you can pretty much assume that they're going to lose 35% of their overall cycle life just due to that temperature. Cold temperatures affect capacity, but when the batteries warm up, that temperature, that capacity returns. So if you're actively operating a battery and the temperature is negative 9 degrees Celsius, you're going to lose 63% of your capacity on that battery bank. Okay, and so you want to be really careful with that, because if you do size that system on Ontario and you put in 1,000 amp hour battery bank and you haven't considered the colder temperatures in the wintertime, what'll happen is that the customer will have to run their generator more often in the wintertime than you anticipated, and that's going to cause problems with your customer. Lastly, my slide is misbehaving on me here, so I apologize for that. Not understanding a 12-volt battery bank, a 24-volt battery bank, and a 48-volt battery bank. A watt is a watt is a watt is a watt. So in this particular case, we have 3 systems: a 12-volt system at 3,000 amp hours, a 24-volt system at 1,500 amp hours, and that should be a 48-volt system at 750 amp hours. I got to start checking my my typing better. So that is supposed to be 48. I apologize for that. I will fix that for next time. They're all 3 different battery banks, right? Well, if we were in a real group, I would make you raise your hands, but unfortunately, I can't make you raise your hands at webinars. But they are the same exact system. Okay. And so that's watt hours, watt hours, watt hours. And so I have a 12 volt, 24 volt, and a 48 volt system. These are the exact same systems. The only difference is at this voltage. And so I personally don't really touch much 12 volt stuff anymore. 12 volts fine if it's a cabin out in the woods and it's 1 or 2 people living out there and you're not pulling a lot of power. But if you're putting in a single family home with a big battery bank, big solar array, 48 volts is the way to go all the way. 20-volt systems are nice because supposedly you don't need as many batteries. That's actually kind of a misnomer. It can cause problems with the system design, so you want to be cautious with that. But 48-volt systems are definitely the way to go in those types of setups. All right, so at this point, I'm going to pause, see if we've got any more questions. It's been a pretty quiet crowd today. There's not many questions other than the one that was already sent in. If anybody has any questions, I will go ahead and wait for about 30 seconds here. While I'm waiting, I want to thank everybody for coming. I appreciate your time and coming to listen to me. Hopefully this made some sort of sense. We're going to probably keep doing these about every 2 weeks. I don't see any questions yet, so again, I'm going to go ahead and go back to my contact information. Oops. I'm going to go back into my contact information here and give you my contact information. If you do have questions and you want to ask those questions offline, feel free to go ahead and email me or give me a call. This is my contact information. Feel free to email me or give me a call. Again, I want to thank for everybody for coming and attending this webinar. Again, we'll have another one next Wednesday, or sorry, the Wednesday after next. And I want to wish everybody a good week. Thanks for attending. Oh.